So you may be thinking that it's a little funny that we call this operation that we're learning about matrix multiplication, because in a lot of ways it feels pretty different from standard multiplication with just ordinary numbers. So the reason why we call it matrix multiplication is that it shares a lot of properties that standard multiplication with numbers has. Okay, and for the most part, I'm not going to prove these, but I do want you to be aware of them. So we have the distributive property. We can distribute a matrix from the left or from the right. We have associativity. That is, if we're multiplying three matrices together, it doesn't matter if I multiply the first two first or the last two first. Okay. And same is true for scalar matrix associativity. Doesn't matter if I do the scalar multiplication first or if I multiply the scalar in first. Okay. The one here that may require a little bit of explanation is the last one. We have a multiplicative identity, which we call matrix I. Okay. So we have this property in standard multiplication too. If I take any number, any scalar value k, there's a number that I can multiply by that will make sure I have this same value again when I'm done. Specifically, if I multiply by 1, I just get the same number back, right? If I have 1 times 17, I get 17 back. What we're saying is that we have that same property here with matrix multiplication, that if I multiply a matrix by this other mysterious matrix, this identity matrix, that I get the same matrix back when I'm done. Okay? So this mysterious matrix, the identity matrix, comes in different sizes, but it's always a square matrix. So sometimes if we aren't picky about its size, we'll just call it I. But if we want it to be a particular size, we want to be clear that it's a particular size, call it I sub n. So I sub n is an n by n matrix with ones down its main diagonal. And zeros everywhere else. Okay, so it looks like this. I sub n is equal to the matrix with ones down its main diagonal and zeros everywhere else. Okay? So let me give you an example just so you could be convinced of this fact. Okay? Let's let A equal to the matrix 3, 2, 1, 0, negative 9, 4. Okay? Now, if I want to multiply A by the identity matrix right here, notice since A is a 2 by 3 matrix, as 3 columns, then in order to make the multiplication make sense, my identity matrix needs to have 3 rows. So this better be an I3 identity matrix. Okay, So an I3 identity matrix, that's a 3 by 3 identity matrix, 3 rows, 3 columns, with 1s down the main diagonal, 0s everywhere else. And if I multiply these together, I'm going to get a 2 by 3 matrix when I'm done. So first row, first column, I get 3. First row, second column, I get 2 when I take the dot product of those. If I take the dot product of the first row, third column, I get 1. Right? On to the second row. Dot product of the second row, first column, I get 0, 0, 0. I get 0. Dot product of the second row, second column, I get 0 plus -9 plus 0. So I get -9. And dot product of, and to get element in the third row, second row, third column, I take the dot product of the second row with the third column. Dot product of those two vectors is 4. Which is the matrix I started with. Okay? Now, what if I go the other direction? Well, notice if I do this matrix multiplication is undefined, right? Because this is a 3 by 3 matrix. The identity matrix I sub 3 is a 3 by 3 matrix, 3 rows, 3 columns. But A is a 2 by 3 matrix. In order for the matrix multiplication to be defined, I need the matrix on the left side to have the same number of columns as the number of rows on the matrix on the right side. Okay? So this matrix multiplication isn't defined, but I can find an identity matrix that is defined on this side. Since A has 2 rows, I need to multiply by matrix I2. So this would be the 2 by 2 identity matrix, and now the matrix multiplication will be defined. The 2 by 2 identity matrix, 1's along the main diagonal, 0's everywhere else. So this is a 2 by 2, this is a 2 by 3. My resulting matrix will be a 2 by 3. Okay. And so first row dotted with the first column gives me 3. First row, second column gives me 2. Dot product of the first row with the third column gives me 1. Dot product of the second row with the first column gives me 0. Dot product of the second row with the second column gives me -9. Dot product of the second row with the third column gives me 4. Okay, so I again get A back. The trick here is that the identity matrix needs to have the right number of dimensions to make the multiplication make sense. Okay, in this statement up here, notice we're not picky about the number of dimensions. We don't say it. The implication here is pick whatever number of dimensions for I will make the multiplication make sense. Okay, so maybe it's a 3 by 3 on this side and a 2 by 2 on this side, but you'd pick whatever identity matrix will make the multiplication defined.